Welcome to Ask and Learn.
Okay, so in this problem, you're given, basically there's two shells, an inner shell and an outer shell, and then they have radiuses R1 and R2, and then you want to find the electric field here, somewhere in between at 4 centimeters, and then on the outside. And you're also given the linear charge density. Oops, not the total charge. There's like a delay in the eraser. I guess I just try to make less mistakes. We'll see. Oh, not sigma. Why did I think it was sigma? Thinking about making mistakes can make you make mistakes. Okay. So we're actually given lambda inner and lambda outer. Great. So basically, to find the electric field within here, it only depends on what's going on inside. That comes out from Gauss's law. I explained it in more detail for problem 29 in this chapter, if you wanted to look at that video. But I'm going to just shorten up and say we're going to completely ignore the outer surface and only focus on the inner surface. And again, you can make a Gauss's law argument for that. And I'm sure it's also written up nicely somewhere if you Google. So it'd be, if we solve it through Gauss's law, making our Gaussian surface through this radius. So the first one we're considering is, I believe it's 4 centimeters. Yeah, so if we do that, then we can kind of draw this Gaussian surface here. And then it really becomes the same physics problem of finding the electric field due to an infinitely long wire. And then I'll just quote the result from that, which is the linear charge density of the inner divided by 2 pi r, the position that you're at. So it doesn't depend actually on the radius at all of R1. It doesn't depend on R1, divided by epsilon naught. Now is a good time to write down the givens. So lambda inner is 5 times 10 to the minus 6 coulombs per meter. Lambda outer is minus 7.0. Oh yeah, that was 0.0. Oh, so sorry for the slop. Times 10 to the minus 6 coulombs per meter. Is there any other givens I should write down? I'll just write it here because it's specific to A. And then, and let me write in the r hat direction. So it's radially outward. This is just, again, quoting this result. And now I'll just say that r is equal to 4 centimeters, which is 0.04 meters. And so if you plug that in for r, and then this in for lambda inner, maybe you'll get what I got, which is 2.2 times 10 to the 6 newtons per coulomb. For B, they're asking about the electric field at a R outside the whole system. So that's at, I think it's at 8 centimeters. And so you just want to do really exactly the same thing. So I'll just write that down, same except lambda I, obviously. Not obviously. This is, so now if you constructed your Gaussian surface here, you would just consider the total charge on the inside. And the total charge on the inside is given by, the total linear charge density within a Gaussian surface going through this R on the outside would include both the charges from the inner and outer shell. And so the total charge density is going to be minus 2.0 times 10 to the 6, minus 6 coulombs per meter. And we also need to use a bigger radius. So R is going to be 0.08 meters now. And if you do that, you might get what I got, which is that E equals minus 4.5 times 10 to the 5 newtons per coulomb. And then that's points in, hence the negative. I'll put the little R hats here to make it, formally correct. And then I'll write down formally that this points out because this is positive in the R hat direction. The R hat vector points radially from the inside.